Hi everyone! In today's video we are going to be doing materials in mechanics, specifically in physics A level. So this applies for AQA, EdXL, Cambridge, whatever syllabus you're doing. This video can be really helpful for you. And we're going to be going over density, springs, deformation of solids, as well as more about stress and strain. So that pretty much includes Young's modulus and all that stuff. So it's a pretty straightforward topic and it shouldn't be too bad. And we're going to start with density in this video, as well as springs, specifically Hooke's law. And then we're going to go on to deformation and whatnot in the next video. So let's get right into it. So we'll start off with density and its measurement. The density of a substance, I'm just going to bring out my pen. Density is defined as mass per unit volume. Mass per unit volume, or mass over volume, whatever. And for a certain amount of a substance of mass m and volume v, so mass is m, volume is v, and you have to write the v a little bit differently. It's kind of like that, so as to not get it confused with voltage or whatever. Its density is p, which is pronounced rho. So it kind of looks like this. It's pretty much just like, you draw it a little bit differently. And it can be calculated using this equation that we've just written, which is density equals mass over volume. And when you rearrange it, you can get V equals M over P, or M equals PV, etc. So we're going to be looking at how to figure out density, because this is a really common question. And you might have done this in GCSE, you might not, but regardless, we're going to go over it. So the first one, which is the easiest one, is a regular solid. First, so I'm just going to kind of give it a subheading, measuring density of items. We're going to start with a regular solid. For this, we are going to measure its mass using a top pan balance. Which is essentially just like a little scale, like an electric kind of scale. And then the second step is we can measure its dimensions. Using a micrometer or a vernier caliper, which is another kind of measuring instrument. Now, and then we're just going to, we're pretty much just going to input it into the equation that is right here and get our value for density. Now, the reason why we use a micrometer or a vernier caliper as opposed to a standard ruler is because they're a lot more, they're going to give us a more accurate value, and they can measure the dimensions a lot more precisely. So that is for the regular solid. The next one that we're going to be talking about is for a liquid. For this one, you can measure the mass of an empty measuring cylinder as your first step. Empty measuring cylinder. For our second step, we are going to, for the second step, we are going to pour the liquid in and measure the volume of the liquid directly. You want to pour the maximum amount of liquid possible to reduce the percentage error. So max volume of liquid to reduce percentage error. And we've talked about percentage error before, but it's essentially the greater your quantity is, so whether that's a mass or a volume, then the less the percentage error is going to be because we're dividing it by the quantity. So yeah, and then you can measure the mass of the cylinder and liquid to calculate the mass of the liquid. Measure mass of cylinder and liquid to get M, and then you just input it. So when you're measuring your mass of your cylinder and your liquid, you obviously have to subtract the initial mass of the cylinder in order to get just the mass of the liquid itself. Our third kind of measurement that we could be dealing with is an irregular solid. So for this, I feel like it's a little bit more tricky. You measure your mass of your object. Again, this is just done on your top pan balance. Immerse it on a thread in a liquid in a measuring cylinder. Immerse and fully submerge. Make sure it's fully submerged in liquid in measuring cylinder using thread. And then calculate the density via mass over volume. So this is actually called a displacement method, and it's a pretty common method. We've learned about this in GCSE. Next, we're going to be talking about the density of alloys. And with that, we should be done with this subtopic. And this chapter has, I think, about 5 subtopics. Again, they're pretty straightforward, so it's nothing to worry about. So an alloy is, did I write allows? Alloy, okay. An alloy is a mixture of 2 or more metals, which is, again, we've learned about this in chemistry as well. For example, you could have like brass, which is a mixture of copper and zinc. And the benefit of having an alloy, you don't really need to know this here, but essentially because we're mixing up different elements, we're going to have different sized atoms. And as a result of having different sized atoms, some atoms are going to be larger, some atoms are going to be smaller. As a result of this, the layers of atoms are less likely, or it's going to be more difficult for the layers of atoms to slide over each other due to the fact that the sizes of the atoms are different, and it causes disruption between the layers, which can result in the mixture of metals being much stronger than the individual metal itself. So if we look at steel, I think it's a mixture of, I honestly don't know, iron and something, but it just, the fact that it's a mixture makes it a lot stronger. So for an alloy, the kind of process of calculating the volume is a little bit more tricky. Let's look at a alloy X, and it is made up of A and B, metal A and metal B, right? So we are first going to do, if the volume of A, V of A is VA, then mass of A is the density of A times the volume of A. This is just from the rearrangement of the equation, where this is, again, the density. And then we're going to do the same thing for B. So V of B is VB. Should have done a tiny b, but it's fine. And therefore mass of B is rho B VB. So therefore mass of alloy M, or alloy X, sorry, which is the mixture, equals rho A VA plus rho B VB. And therefore, because we know density equals mass over volume, which equals rho A VA plus rho B VB, which I've just got from up here, over the total volume, and then you can kind of just, you can separate them into rho A VA over V plus rho B VB over V, but I'm just going to kind of leave it at it as is. So that is pretty much the process of finding the density of your alloys. We're going to move on to calculating, we're going to move on to 11.2, which is springs. So we're pretty much done with this subchapter. Again, it's so straightforward and small. I feel like that's a nice color. Let's look into 11.2, which is springs. And then with that, we're going to conclude this video. And in the next video, which is going to be part 2, I'm going to be going over the other topics. So Hooke's law. Hooke's law states that a stretched, I forgot to speak there. A stretched spring exerts a pull on the object holding each end of the spring. And this pull is referred to as our tension in the spring. And it's equal and opposite to the force that is needed to stretch the spring. So just to kind of rephrase that, a stretched spring will exert a pull on the objects that are holding either end of the spring, and this is known as tension, and it's opposite and equal to the force that is needed to actually stretch the spring. So therefore we can kind of deduce the fact that because it's opposite and equal in magnitude, we can deduce that it is actually going to be the tension of the object. So the more a spring is stretched, the more a spring is stretched, the greater the tension that is within it. And you can plot your tension against extension to get a graph, and the graph shows the force needed to stretch a spring is proportional to the extension of a spring, and this is known as Hooke's law. So we can plot force against extension to get a graph, and if for this graph what is this? The force the force is proportional to extension then the object obeys I just wrote Hooke's law. Hooke's law. Hooke's law was pretty much a law created by Robert Hooke. He was, I believe, a 7th century scientist. And the law itself is that Hooke's law states okay, this is Hooke's law. And it can also be written as force F equals K delta L, which is, we're going to elaborate on this in a second, but if we kind of go back to the law itself, a force needed to stretch, oh god, this is an awful color for a highlighter. Absolutely awful. Okay. A force needed, I don't know what's going on here. A force, see, you know, needed to stretch a spring is directly proportional to extension of a spring from its natural or initial length, whatever you want to call it. And yeah, so let's pick a nice color. I feel like orange is nice. So when we look at this equation that I've written right here, let's elaborate on it. K is the spring constant. And delta L is extension. From initial length, and then force is obviously force. So the greater the value of K is also known, by the way, as stiffness. So the greater the value of K, the greater the value of K, the stiffer the spring. And this logically does make sense because if you think about, so as K increases, right, for an extension, say I need to extend my spring by a length of 5 centimeters, right? Or let's make it 10 centimeters. If I keep that 10 centimeters constant, and I look at force and extension, and I look at force and springs constant, as springs constant increases, right, so my length, my delta L is a constant of 10, and say I have a springs constant of 5 initially, then the force required will be F equals 5 times 10, which equals 50. However, if I have my springs constant to be more, so say it's like 10, then again, I'm keeping the constant of my extension, which is 10 again, then it's going to be 100. So the force required is 100 newtons. So obviously, if you need more of a force to pull something, then that means that it's stiffer, or that means that the spring itself is, it's not as easy to pull. So essentially that's just what they're trying to explain from this, and you can kind of look at it in this logical way and deduce the fact that as your spring's constant increases, that pretty much just says that your spring is more stiff. So the unit of K, by the way, is in Newton per meter, or Nm to the power -1. A graph of F against delta L, which is extension, is a straight line passing through the origin, which basically just means it's proportional. Origin, and this only applies obviously for elastic objects or for springs. If a spring is stretched beyond elastic limit, so beyond the elastic limit, it does not regain its the spring will not regain its initial length. So we can just say that force and extension are no longer proportional. And in AS A-level math, we can, you might come across Hooke's law, but it's slightly different. But we're not really going to be talking about that right now because we're looking at physics. So our last little kind of part of this chapter, of this subunit, is spring combinations. So you could have springs in parallel, you could have springs in series, and you could also have the energy stretched in a spring. However, I do feel like that part of this sub-chapter kind of goes on, or kind of goes hand in hand with deformation. So we're pretty much going to wrap it up here. And then in the next video, we're going to be going over the little part of springs that is left. We're going to be going over deformation of solids, which is 11.3. And that's literally it. It's a really short chapter, and it's nothing to worry about. We also have to talk about stress and strain, I think. And with that, it's just going to be concluded. I hope you guys enjoyed, and if you have any other suggestions, please feel free to let me know. And stay tuned for the next video in which we're going to be covering 11.25, 11.3, and then we might go into 11.4, or I might make that a separate video as part 3.